Okay, and then I am going to turn it over to John, our resident expert on all things heat exchangers. So take it away, Ziggy.
Well, thanks, Max, and good to be with you folks again. I understand we've got a great size audience, and we've got another broad topic that we have covered in detail in the hydronics that Max was talking about. And I'm going to go through a good portion of that today. But again, for more detail, definitely take a look at Hydronics 29. So what we're going to do, we're going to kind of look at a very brief history of heat exchangers. I mean, heat exchangers are pervasive in our lives today. We're going to be talking about them in the context of hydronic and plumbing systems, but every day we interact with equipment, refrigerators, air conditioning systems, vending equipment. All these devices have heat exchangers in them. So we will focus more on the hydronic and plumbing applications, but we are going to talk about heat transfer fundamentals. These would apply to all types of heat exchangers. And it's important to understand these fundamentals because as you apply a heat exchanger, certainly differences in things like temperatures and flow rates, as well as the physical configuration of the heat exchanger can and will influence the performance of those heat exchangers. We want these devices to be long lasting. We want them to remain close to, if not at, their original specifications. So keeping debris out of a heat exchanger, for example, is an important installation detail. And we're going to wrap up today's session looking at some applications of heat exchangers. So again, historically, probably one of the earliest types of heat exchangers, and I'm sure many of you have come across this Roman hypocaust photo or similar photos. The Romans basically built pillars, and then they would build these masonry floors over the pillars. They would start fires on one side of the building, and they actually would channel the flue gases from those fires in this space under the floor. And in a form that is heat exchange. We're taking heat out of combustion gases, we're passing it through that masonry floor, and we're using it for a useful purpose to heat the space up above. A wood stove is another good example where we're exchanging heat between flue gases and heated space. And obviously we're trying to do that with, ideally, with zero mixing between the flue gases and that heated space, okay? Some early applications, here's where there's a wood or a coal-fired stove, basically, that incorporated a water jacket and a device called a range boiler. And I'm not sure where that term came from, but basically it's just a tank. And these used to be just galvanized steel tanks. And you can see it's installed above the wood burner, and there was no circulator because there was no electricity at this point. And this relied strictly on natural convection heat transfer to take the heat from the flue gases, transfer it through that metal wall of the water jacket, and then ultimately put it up into that tank. There's a pretty interesting heat exchanger from the early 1900s. That's a radiator out of a Model T. And actually, for its time, it was pretty well engineered. You can see there's a lot of contact area there between where the fluid, the water in the radiator, and the air passing through it would be. And those were actually non-pressurized. They did not have a cap like the caps that we have on modern radiators. So at times the water would actually boil and evaporate from that, and the drivers learned to carry extra water with them to fill it back up. Cast iron boiler technology, a cast iron section. These have been around for decades. They're still being used. This is basically a heat exchanger between flue gases, whether it's from an oil burner or from a gas burner, and water that would be inside of those. And certainly a cast iron radiator, example of heat exchanger. This is an early wrought iron installation for floor heating, way before we had PEX tubing, even before copper tubing was used. But essentially a heated floor is a heat exchanger. We're passing warm water into it, and we're taking heat, moving that into the heated space. And now we get up into some modern designs, so some large cooling towers. again, transferring heat, unwanted heat out of a stream of water into the atmosphere through these large coils and fans in these cooling towers. And I want to give you an example of a very, very small heat exchanger. These are being used on some high-end microprocessors, basically squeezing more and more switching circuitry into a microprocessor creates more heat. And to extend the life of that product, it's necessary to pull heat off of that. So you'll see there's actually a little copper plate that would be bonded down with a conductive paste onto the top of that microprocessor. And that's actually a tiny little hydronic system. You can see there's a coil, there's a little fan, you can see some copper tubing there. That probably has a mixture of water and alcohol in it, and it would just circulate as necessary. I'm sure there's some type of thermal control that would vary the speed of that fan, but it is a heat exchanger to pull heat off of that microprocessor. So you can see here from the hypercost up to these little microprocessor cooling systems, heat exchanger technology has certainly evolved a lot. So we're going to start off with some categories. Internal heat exchangers. Most of you would recognize this as an indirect water heater. You can see the stainless steel coil in the lower portion of the tank there. We're going to pass a heated fluid, typically from a boiler, through that coil, excuse me, and transfer the heat to the domestic water in the tank. So schematically, this is what it would look like. Now we are using a circulator to push the water through the coil, but inside the tank itself, we're counting on just buoyancy and convection, what's called natural convection, to create the flow that ultimately scrubs the heat off the surface of that internal heat exchanger. And different companies offer tanks that have different configurations of these internal coils. The most common one would be a single coil at the bottom. There's several different brands of indirect water heaters in the North American market that have basically that configuration. There are some that have an upper coil, and I'll show you an example where we'd use just a tank with an upper coil. And then some manufacturers actually offer both an upper and a lower coil. In some cases, they are on independent circuits, and in other cases, they're actually connected so that you have one larger surface area internal coil. Now, in some code jurisdictions, depending on what the fluids are, if it's an antifreeze fluid and you're exchanging heat with potable water, some code jurisdictions require what is called a double wall heat exchanger. And if you look at the cross section here, what's going on with a double wall heat exchanger is you actually have an intermediate space that has little grooves in it. And the idea here, the concept is, if either fluid leaks through the wall that is separating it from the other fluid, that fluid is going to come through those grooves, and ultimately it's going to leak outside of, in this case, outside of the tank. So it would leave a visual evidence that there is a leak, there's a failure of the heat exchanger. Double wall heat exchangers do have lower performance, thermal performance, than single wall heat exchangers because there's more resistance to the heat transfer, both in terms of the thickness of the materials, the amount of material, and the presence of those grooves there. But where they are required, I know, for example, I believe in the state of Wisconsin, they were required in solar domestic water systems, even if it was a non-toxic antifreeze. The best advice would be to just check with local mechanical codes. If you're working with a tank and you are working with an antifreeze solution, to see if there is a double wall heat exchanger requirement. Here's an example of a tank where we've got a heat pump water heater as our primary heat source. So we're taking water from near the bottom of that tank, we're circulating it up through some type of heat pump unit to add heat to it, putting it in the top of the tank. Now, if the heat pump is sufficient to keep up with the demand of domestic water, there's actually no need to operate the supplemental boiler. But if the heat pump can't keep up with the load, or if the heat pump is down for service, this configuration shows an auxiliary boiler tied into that upper coil. So again, the water in the fluid circuit going through the auxiliary boiler is completely separated from the potable water by that internal coil. And we want that coil up at the top because that's where we're going to inject the highest temperature heat. And that is also where the water is going to leave the tank and go off to the load. So we want to make sure the water at that portion or that upper portion of the tank is hot enough to meet the requirements of the load. Here's another example. In this case, the upper coil is a heat extraction coil. So it would typically be made out of copper, or more commonly today would be stainless steel. This is actually a pellet boiler system, and the tank is set up as what we call a two-pipe buffer. The pellet boiler is adding heat into the tank. You can see there's a takeoff just before the pipe enters the tank here. This goes off to a load, a space heating load. But for domestic water, again, we want to isolate domestic water from the what I call system water that would be used for space heating, and that upper coil is doing it. It is important to have a thermostatic mixing valve on a system like that. Pellet boiler systems can get that water in that tank up in a range of 180, 190 degrees Fahrenheit. And under those conditions, you're going to have incredibly good heat transfer through that coil and some very high scalding hot outlet temperatures. So that thermostatic valve is there to make sure that the temperature going to the plumbing system in the building doesn't go over typically 120 degrees Fahrenheit. And then finally, here's another system. This is a solar thermal system with an auxiliary boiler. The solar portion of the system is a closed loop. It would operate with an antifreeze solution. And you can see the solar collectors here are piped through the lower coil. And the reason for that is we want the solar BTUs to be added at the lowest water temperature, because that's going to improve the efficiency of the collector. So we're basically trying to keep the heat exchanger immersed in the cooler water near the lower portion of the tank. And then if necessary, you see the auxiliary boiler over here on the right with a circulator that can turn on and add heat. Again, you can see the heat input from the auxiliary boiler is going into the upper portion of the tank. And then the inside the tank, we have that upper coil. That coil would be, again, either copper or stainless steel. It would have the potable water in it. Again, you'll see a thermostatic mixing valve to make sure that we aren't sending excessively high water temperatures out to the plumbing system. And then this tank also serves as a buffer for a zoned hydronic space heating system. So there are a lot of potential applications for internal heat exchangers in hydronic systems, depending on what the loads are and also what the heat sources are. Here's another example of internal heat exchangers. These are large non-pressurized thermal storage tanks. This particular tank would come in what I call a knockdown configuration. It's basically put together on site, and it's large, 800 gallons of storage. That would be very impractical to try to move into an average basement if it was pre-assembled. And the common approach, actually for several decades, has been to use these large copper coil heat exchangers that are immersed in the water in the tank. You can see the connections down here in this photo. The connections are near the top of the tank. They're just above the water line. There is a seal there to minimize any evaporation from the tank, but those connections are actually not designed to be submerged. And that sets up some interesting pressure dynamics. I won't get into them, but it is possible to do this, certainly. Over on the left, you'll see there's two coils in that tank. The coil on the left is heat input. And this white arrow is showing the direction that water inside the tank would be flowing after it absorbs heat from that coil. It's going to expand, its density is going to decrease, and it's going to rise. And pay attention to the direction of the flow in that coil. You'll see the hot water from the heat source comes in, and it goes opposite the direction of the water in the tank. And this is called counterflow, and it's a very important concept. We'll be talking about it quite a bit during the webinar today. Now, what are the practical concerns here? Well, the heat transfer from the surface of the coil to the water in the tank is by what we call natural convection. Natural convection is relatively weak compared to what is called forced convection. I've got more slides that we're going to get into this a little deeper, but because of the fact that we're relying on natural convection, we have to have a lot of surface area to get the heat transfer rate that we're looking for. And if you look at that photo there in the lower right, you can see there's a lot of copper in that tank. And the modeling of the performance of a coil like this from a theoretical standpoint is very complex. Some of you may have worked with some of the empirical relationships dealing with natural convection, but it gets very mathematically deep. And even then, you're modeling simplified situations. You aren't necessarily accurately modeling the presence of multiple coils in the tank or the influence of one coil to the other. One of the things that I have found over the years in looking at systems like this is that it's very hard to find good engineering sizing information on these coils. You may find snapshots of performance if the tank water is at temperature X, and if the water coming into the coil is at temperature Y, then you're going to get this rate of heat transfer. But that's a snapshot. What we need is a wide spectrum of performance, and I have found that hard to come by. So I'm not a huge fan of these simply from the standpoint that the performance modeling is somewhat of a guesstimate. And these coils are expensive, especially today. Each of those coils is probably in the range of $1,000. So yes, we can guess high, but we're adding quite a bit of cost to the system. And there are other ways to add heat and extract heat from this type of a tank. And again, we're going to get into that. So now we've talked about internal heat exchangers, essentially coils inside of some kind of a tank. The other type, and the much broader portion of the market, is external heat exchangers. And there's basically three common designs for these. The shell and tube heat exchanger over on the left here. I'll show you some examples of that. In the middle, what's called a shell and coil. Essentially, the difference is just how the tubing is configured inside this closed pressure tight shell. And then finally, over on the right, a flat plate heat exchanger. And for most hydronic applications today, especially residential light commercial applications, and I would say, in all fairness, even today with larger applications, the flat plate heat exchanger is really starting to dominate the market in space heating and cooling applications. There are other industrial applications where, for example, a shell and tube heat exchanger has higher pressure and temperature ratings that may be necessary in a very high temperature, high pressure environment. But the flat plate heat exchanger has really come to dominate the geometry of heat exchangers in the HVAC market today. Now, a tube-in-tube heat exchanger. Here's an example of one. It's a really simple idea. We have one tube inside another tube. The inner tube has one fluid passing through it. The space between the outer and the inner tube has the other fluid. So we call that the shell or the outer tube. And if you do some calculations, you'll find that to get the type of heat transfer rates that we need for heating buildings, it's not practical to have this in one long assembly. It would be very, very long. Think 50 feet, 100 feet plus. So what's commonly done is to take this geometry and then roll it into a coil simply so it can fit inside a cabinet. And that type of heat exchanger is used a lot in heat pumps today as the heat exchanger between a liquid like water or an antifreeze solution and geothermal loop and a refrigerant that is part of the heat pump circuit. So a coaxial tube-in-tube heat exchanger is a common design. Back to the shell and tube, essentially what you've got, and the picture here shows it a little bit better. You have a tube bundle, and it can vary in terms of the size of the tube and the number of tubes, but these tubes all connect on both ends, typically to a plate or a header, a bulkhead, I guess is the proper term for it. And that's a pressure tight seal. At the ends of the heat exchanger, we have these chambers of the lower manifold, the upper manifold, and the fluid comes in, and these chambers essentially just distribute that fluid through the tube bundle. The fluid moves through the tube bundle, and then it's collected by the other chamber at the other end of the heat exchanger. That would be called a single pass tube and shell heat exchanger. The other fluid, if you see these two ports on the side of the shell here, the other fluid comes in and it flows around the outside of the tubes in that space, and then it's collected at the other end of the shell and exits the heat exchanger. Again, the two fluids for best performance would be going in opposite directions. Now, down at the bottom here, these heat exchangers, these are multiple pass tube and shell heat exchangers. So instead of having a manifold chamber on the opposite ends of the shell, both the inlet and the outlet for the tube bundle are on the same end of the shell. So essentially, the internal geometry sends flow down through the tubes on one side. Those tubes make a U-turn at the end of the heat exchanger, the other end of the heat exchanger, and then the flow comes back and it comes out the other end. So that would be a two tube pass, single shell pass heat exchanger. And actually, there are even more than two. There are designs that can go to 3 pass, 4 pass in both the tube side and the shell side, depending upon, again, what's the heat transfer requirement. So that gives you an idea what a shell and tube heat exchanger looks like. Now, a shell and coil heat exchanger is a similar concept, but instead of having several individual tubes that are bundled with a bulkhead plate at each end, it's typically a single coil, a helical coil, and that coil typically is copper. And you can see in some cases, like on the left here, that's a sealed heat exchanger. Once that is manufactured, you're not getting back inside it, which may not be any issue. But if there is a problem, if there's a leak in the coil inside there, basically it's a throwaway, or I should say a recycle. You're not going to get in there to repair it. Over on the right is a variation on that. This is one that is serviceable. This is where the coil is actually sealed into a bulkhead plate, and that plate is sealed into the shell of the heat exchanger with a gasket and several bolts, so it is removable. And here's an example of a shell and coil heat exchanger. We typically call these reverse indirect water heaters. These are on the market. In fact, there's some new ones just introduced to the market in the last couple of weeks here. What we have are multiple copper coils that are connected to headers at the bottom and at the top. And in this case, potable water, cold potable water, is going into the bottom header. It splits up, flows up through these coils, collected by the upper header, and it goes out to a domestic hot water load. The heat source, typically it's a boiler, although it could be anything. Heat source is injecting hot water into the shell here. And again, it flows down through and comes back out. Now, this is fundamentally a heat exchanger, but I call it a heat exchanger with lots of thermal mass because there's quite a bit of water mass in that tank, and that's good because that allows for domestic water to be heated at times when there's no heat input from the heat source. Okay? And then that brings us up to flat plate heat exchangers. And the concept here is pretty simple. It's a stack of stainless steel plates that are going to be brazed together. So they're metallurgically bonded both at the perimeter and also internally. And if you look at that upper left diagram, you see one fluid comes in and it passes through every other space. So think of it as a multi-layer sandwich. If we were to number those spaces between the plates, if we just numbered them 1, 2, 3, 4, and so forth, one fluid is passing through space 1, 3, 5, 7, and so forth. The other fluid, the blue, would be passing through space 2, 4, 6, 8. So we have alternating channels, and the beauty of this design is it puts a lot of surface area in a relatively small package. And that is good because that increases the heat transfer capacity capability of the heat exchanger without using a lot of additional metal or requiring a much larger space. Several companies make these. They're in a wide variety of configurations. This is a photo just to show you. I just lined up 3 heat exchangers that I have in the office here. That big one, the plate size is nominally 5 inches wide, 12 inches tall, and there's actually 100 plates in this stack. So we would call that a 5 by 12 by 100 plate raised plate heat exchanger. That again, once these plates are arranged and pressed together and brazed, they're actually baked in an oven to do the brazing. At that point, that's a sealed unit. Any failure internal to that unit would require replacement. Next to it is just a smaller version. It's the same nominal plate size. It is from a different manufacturer, so I use the word nominal. These are not exactly 5 inches by 12 inches. But you can see it's not as deep. It's a 40 plate stack. And then finally, the little guy there, that's a 3 inch by 8 inch by 10 plate heat exchanger. And depending on what the water temperatures are or the fluid temperatures and flow rates, that small heat exchanger may be all you need. But be careful. One of the things you don't want to do is assume that a small heat exchanger will always do your heat transfer rates for you. Like anything else in hydronics, these need to be sized, and we'll talk about that. Now, here's the big brothers to the brazed plate heat exchangers. These are called plate and frame heat exchangers. Same concept, although this is a unit that is not permanently sealed together. The stainless steel plates here have gaskets around their perimeter, and the idea is basically we're going to assemble a sandwich, a stack of these plates, and you'll see there's a carrying bar up here at the top, and these plates basically slide down onto this bar, and it suspends them almost like a coat hanger, if you will. And once we have the required number of plates hanging from the bar, the pressure plates, these are thick steel plates. And if you look at these photos here, you can see these are thick plates. Sometimes these are on the order of 1.5 inches, 2 inches thick, depending on the size of the heat exchanger and the pressure rating. These plates act as kind of the bread on the sandwich. You're going to push the plates together. There are bolts, tightening rods actually that go through the plate all the way from the back to the front. You can see them there. And these are going to be torqued down. The nuts on these are going to be torqued down to specific torque settings, and that creates a pressure tight assembly. Now, the nice thing about these is that they can be disassembled if necessary. That's a lot of work. We don't want to be in a position where we have to disassemble something like this on an annual basis to clean it. We want to deal with the dirt issue a different way. We want to collect the dirt before it goes into the heat exchanger. But if necessary, they can be disassembled, whereas a brazed plate, you can't do that. The other thing about these, you'll actually see in the upper left here, these rods extend out beyond the back plate, and so does the carrying bar. That would allow the heat exchanger to be expanded in the future. This photo in the lower right shows it pretty good too. The red that you see here, these are just plastic tubes that are put over those threaded rods for safety. But you can see there's quite a bit of space left in that frame. So if that building is expanded in the future, the loads change, whatever, if it's necessary to increase the size of that plate frame heat exchanger, it's just a matter of pulling the back pressure plate, adding the additional plates to it, and then reassembling it. The upper right just shows a heat exchanger that has insulation added to it. A large plate and frame like this would have a lot of surface area. Obviously, that would throw a lot of heat into a mechanical room if it's operated at high temperatures. So there are different packages available for insulating these heat exchangers. Now, fan coils and air handlers, these are fundamentally heat exchangers. So a fan coil is taking the fluid from a hydronic heat source and it's passing it through the coil, which is copper tubing, aluminum fins. We've got a blower down below here, which is blowing air past it. So we're exchanging heat between that fluid and the room air. And we call that fan coil. They can be wall mounted. Here's one, and I'm sure many of you say, well, I've seen these. These are ductless mini splits. Well, it's basically the same thing as a ductless mini split indoor unit, except the coil is set up for water or a water antifreeze solution as opposed to a refrigerant. Other than that, it's identical. It has the blower, it has the coil, it has controls. You turn it on and off with a remote. Air handlers are another geometry with the same idea. We have a coil, copper tubing, aluminum fins, okay? And we have a blower. The difference here is an air handler is typically set up to be connected to a ducting system, whereas a fan coil is just bringing in room air at the bottom and discharging it out. Down at the bottom here, this is this is about a nominal 35,000 BTU per hour rated coil. That's actually being used in a chilled water cooling system where a heat pump is supplying chilled water through this insulated tubing. And you can see the return duct on the right and then a discharge plenum over here. And this is providing whole house cooling. And then air handlers are also available in vertical configurations. So you'll hear the term horizontal air handler, vertical air handler. Many of the products that are on the market now can actually be configured for either one. You can actually pull the coil out, change a couple things around, and the same cabinet could be applied in a vertical or a horizontal configuration. And you can see the coil here. There's some zone valves in here that determine when flow goes through the coil, and then you can see the blower motor up at the top here. Air handlers are typically set up as either 2-pipe or as 4-pipe. If you take a look at Hydronics 28, we get into that in more detail. A 2-pipe system with multiple air handlers, the whole building is either in the heating mode or in the cooling mode. Now, within individual spaces, one air handler could be on and another one could be off. But what we can't do with a 2-pipe configuration is we can't heat one room and cool the other room at the same time. With a 4-pipe configuration, we typically have 2 independent coils. They're actually on 2 different hydronic circuits within the same cabinet, and the zone valves determine which coil is active. So in heating, the zone valve for hot water flow allows hot water to go through that one coil. In cooling, same idea, only with chilled fluid. So this allows any individual space that's part of a system with 4-pipe air handlers to be either in heating mode or in cooling mode. And then finally, from a plumbing standpoint, one of the heat exchangers that I think is deserving of more interest is gray water heat recovery. This is basically taking water from sinks and showers and bathtubs, but not wastewater from toilets. All right, we're taking gray water that would go down the drain, and we're sending it down through a copper tube, and that water will tend to cling to the inner surface of that copper tube. And then we're surrounding that copper tube with another coil, a helical coil of copper. And in some cases that is bonded, metallurgically bonded, soldered or brazed to that inner pipe. So it's in effect a double wall heat exchanger. We have the inner copper pipe that carries the gray water, the tube wall there, and then the other tube wall carrying potable water. And that's set up to recover some of the heat. If you think about it, much of the heat in a shower or in a lavatory, it just goes down the drain. So this is scavenging some of that heat and using it to preheat domestic water. In hydronics, there's a better explanation of this, but this is where we're scavenging heat from gray water, and we're sending some of that preheated cool water up to the cold port on a shower valve. It's already got some heat in it, and of course we have hot water coming from the other source. So that actually would reduce the amount of hot water that would have to go into the mixing valve for a given shower head temperature. So we've looked at the geometry of these heat exchangers. Let's take a look at heat transfer. All right. I've talked about these two terms, natural convection and forced convection. And just to differentiate, natural convection is fluid motion due to buoyancy. There's no fan, there's no circulator involved. A thunderstorm is a result of natural convection. Okay. So is warm air rising within a room. Forced convection is where the motion of the fluid is caused by a circulator, or in the case of air, by a fan or a blower. Now, the rate of heat transfer by convection, pretty simple looking equation here. We have a value called the convection coefficient. It's a constant that has some value to it. We have the heat transfer area. This would be the area between where the two, where a solid surface, for example, is in contact with a liquid, all right? And then we have the temperature difference, the average temperature difference between those. So it looks like if we knew the value of H and A and delta T, you know, three numbers, multiply them together, we get the rate of heat transfer. Delta T and A are pretty easy. This one can be very difficult to come up with. The convection coefficient can vary widely depending on the fluids involved and how those fluids, how the motion of those fluids is being created. And you can see here, for example, natural convection with air. The range for this convection coefficient can be from 1 to 5, and it's the units in classic North American units here would be BTUs per hour per square foot per degree Fahrenheit. But if we go to forced convection, where we're using a blower, look at how much higher the convection coefficients can get. That's because of turbulence. Turbulence improves heat transfer. Very important concept. We want turbulent flow in heat exchangers. And then when we get to water, because water has much higher specific heats, higher densities, you can see convection coefficients can be over a much, much wider range. And this can certainly have huge consequences as far as the rates of heat transfer. Okay. And in many cases, we have examples in our HVAC systems of hardware that involves both forced and natural convection. An indirect water heater. We have natural convection of the water in the tank, represented by these white arrows here. Again, heating the water, decreasing density, it causes that water to rise slowly within the tank. And then we have forced convection within the coil because we have a circulator driving that flow. And the overall rate of heat transfer depends on both the ability of forced convection on the inner surface of that coil and natural convection on the outer surface of that coil. And it's very uncommon to find a situation where the limitation in the rate of heat transfer is not created by natural convection. Natural convection is typically the bottleneck to the rate of heat transfer. So we could blast the water through that coil at a very high flow rate, and we wouldn't necessarily see a significant change in the rate of heat transfer because our limitation is not on the forced convection side, it's on the natural convection side. Baseboard is another example. We're pumping hot water through the pipe. We have relatively high convection coefficients on the inner surface of that pipe under normal flow rate conditions, but we have natural convection of the air heat transfer on the fins and the outer surface of that tube. And again, that becomes the limiting factor. Now, as Max was saying, we do look at the questions that you folks submit prior to the webinar. And one of the questions, this is verbatim, does GPM matter through the heat exchanger? And the answer is yes. Okay. Now, high flow velocities, flow rates and flow velocities are related. As one goes up, so does the other. So high flow velocities create turbulence, and that increases convection. All right, so if we look at the cross-section of the pipe and we look at the flow going down through that pipe, we actually have slightly higher flow velocities near the center of that pipe than we do out near the edge. But one of the things that is characteristic of the modeling of heat transfer is what's called a boundary layer. And a boundary layer is a thin layer of fluid within which there's very little fluid motion. There's some, but it's nowhere near as active as the core of the flow stream. And because the slow moving fluid, because those molecules aren't stirring around very aggressively, that you can think of that as almost like an insulating layer between the flow stream and the inner wall of that pipe. So what we want to do with a boundary layer, if we're trying to create heat transfer, we want to minimize the resistive effect of the boundary layer. And we do that by creating turbulent flow. Turbulent flow reduces the boundary layer thickness. Laminar flow increases it. And just as an example, if you look at the heat transfer ratings on FinTube, most manufacturers plot those out at flow rates of 1 GPM, 1 gallon per minute, and 4 gallons per minute. And without exception, you'll find at 4 gallons per minute with the same water temperature, the heat transfer rates are higher. And that's simply because we have a thinner boundary layer. We have better convection inside the pipe that is transferring heat to those aluminum fins. I just plotted out, one manufacturer's data. Now, another important thing to understand about rates of heat transfer and flow velocity, it's a very nonlinear relationship. And what I'm plotting here is the output of a small fan coil unit where we keep the water temperature, the airflow rate, and the air inlet temperature constant, but we vary the water flow rate going through the coil. And so we're trying to just isolate water flow rate and its effect on heat transfer. And you can see when we start at essentially 0, and we start to increase the flow up, the heat transfer rate goes up very rapidly. But as we go to higher flow rates, we're still going up, but we're getting a diminishing return. And by the time we get out here, we're getting very little return on that higher flow rate. And of course, that higher flow rate is costing us in terms of pumping power and perhaps the size of the pump that we're using. So there's definitely a diminishing return on increasing the rate of heat transfer by increasing flow velocity. When you double flow velocity, you do not double the rate of heat transfer in the typical operating range, when we're up in this range here. Down here, potentially, okay? But these are typically very, very low flow rates, okay? When we're in a typical operating range of a fan coil or a baseboard or a radiant floor circuit, increasing flow does increase the rate of heat transfer, but it is not a proportionality. Now, again, I've talked about it, I'll go pretty quick. Laminar flow is basically where our streamlines are parallel. Think of it as a multi-lane highway where the cars don't cross the lanes. And this allows that boundary layer to actually get thicker, and this inhibits heat transfer. Now, if your purpose in designing a system is transporting a heated fluid over a large distance, and you're trying to minimize heat loss from that pipe, laminar flow is good. Laminar flow actually would reduce both heat transfer losses from that pipe, and it would reduce pumping power. But if your purpose is to transfer heat out of that fluid through the tube wall to some load, you do not want laminar flow, you want turbulent flow. Turbulent flow, in its sense, you can think of it as scrubbing the thickness of that boundary layer down and reducing its resistance, okay? Without getting too deep in numbers, you can determine whether you have laminar flow or turbulent flow by knowing things like flow velocity, the density of the fluid, the diameter of the pipe, and the viscosity. And there's a calculation called the Reynolds number for that. You need to know these fluid properties. Hydronics does get into this in a little bit more detail, but the short story of it is you can verify whether a flow of a given fluid at a given temperature at a given flow velocity is going to have laminar or turbulent flow, okay? Now, flow direction, also very important in heat exchangers. We could operate a heat exchanger with what's called parallel flow. This is where both fluid streams are going in the same direction. And this graph up here just shows we're coming in with the hot fluid at some temperature. We're coming in with the cold fluid at some lower temperature. And as we progress along the heat exchanger, you can see these temperatures are coming together. So there's always a temperature difference between the hot fluid and cold fluid, but that may not be our optimal situation. The other choice is counterflow, where the fluids go in the opposite direction. And again, you'll see in the graph, the hot fluid is cooling off as it flows through its chamber, and the cool fluid is gaining heat. So when we look at this, we look at the gap between that upper curve and that lower curve, and obviously it changes a lot along the length of this heat exchanger, and it's also changing down here. So which is better? Is this better? Is this better? Well, we need to know which one gives us the highest average delta T, or temperature difference between the fluids across the heat exchanger. And within heat exchanger theory, there's a parameter called the log mean temperature difference. And if you have a heat transfer handbook or textbook, they all cover the derivation of this. But the formula down here involves knowing the temperature difference between the two fluids at one end of the heat exchanger and the other end. And then you subtract one from the other, and then you divide by the natural logarithm of the ratio of the two. This is, from a derivation standpoint, this is the characteristic. I'd like to describe it as, think of this as the effective average delta T between the two fluids, okay? So here's a quick example. I've just put some numbers on the heat exchanger here for the entering fluid temperatures and the leaving temperatures, if all four of those are known. It's a simple calculation to come up with the log mean temperature difference. And there's a way to prove that you will always get a higher log mean temperature difference with counterflow versus parallel flow. So that's an important takeaway. Anytime you configure the piping for a heat exchanger, whether it's a tube and shell or a flat plate, whatever it is, you always want the fluids going in opposite directions to maximize the rate of heat transfer, okay? Again, there's some formulas. We do a deeper dive in hydronics, but to calculate the rate of heat transfer across the heat exchanger, you would need to know the log mean temperature difference, the internal area, this would be the metal area that is separating the two fluids, and the overall heat transfer coefficient. And just to kind of give you a picture, imagine over on the left here, we have a fluid at some temperature, I'll call it T1. The gray area here just represents a metal wall that separates that fluid from the fluid on the right, the cooler fluid over here, all right? Now, in a perfect world, heat would pass through here and there would be no resistance to that heat transfer. So we would be able to get the cooler fluid up to the same temperature as the hot fluid. But we don't have perfect worlds. We have things like boundary layers, which you can see here, the effect of the boundary layer, because it is in effect thermal resistance, is that's going to reduce the water temperature that is actually against the surface of the metal here. Or if you have a heat exchanger that has a lot of dirt or scaling, you have another resistance here. It's called a fouling factor or a fouling film. It's basically a buildup of some type of debris on the surface of that metal. Ideally, we don't want that there, but in reality, we're going to have it, and it also is going to create some temperature drop. The metal wall itself, most of the metal walls are pretty thin, and they are high conductivity. So yes, there's a slight temperature drop there, but in most cases, it's very small. And then finally, we have the fouling film and the boundary layer on the cool side. So we can think of these various layers as thermal resistances. And if we could calculate how much resistance effect each of those layers has, we add them together just like we'd add our values for insulation, a layer of different insulations. And that lets us determine, indirectly, it lets us determine the overall heat transfer coefficient here. I do want to just point out the fouling factors that are commonly used, or various handbooks have suggested values for these. And if you look at these numbers, they're relatively small, but I want you to see the difference between demineralized water versus, let's say, untreated water. you can see the fouling factor is quite a bit smaller there. So it's important to keep the surfaces of these heat exchangers, the internal surfaces, as clean as possible. Demineralized water is certainly one way to do that. If the makeup water in the system has high total dissolved solids content, you definitely want to treat that water before you put it in the system. And also other debris, dirt debris or iron oxide, we don't want those films to form on the inside of the heat exchanger. Now, typical convection coefficients, I've mentioned already, natural convection is a much weaker phenomenon in terms of encouraging good heat transfer compared to forced convection. And here's an example where I compared a fan coil that when it's supplied with an average water temperature of 110 degrees Fahrenheit in a room that's at 68 degrees, it has a blower in it, and this is a relatively small fan coil. It's 2 feet high and about 2.5 feet wide. This is a scale comparison between a fan coil that's putting out 6,700 BTUs per hour and what would be necessary with residential thin tube baseboard to also put out 6,700 BTUs per hour. And that's 57 feet of fin tube. So this is why baseboard in low temperature systems is difficult as a heat emitter solution. It is very limited by the natural convection on the air side of the fin tube element compared to what's possible with forced convection and a fan coil. So you'll typically find in lower temperature systems that a fan coil, again, with a blower or a fan in it, is going to be used simply because you can accommodate it in the space. Imagine trying to put 57 feet of baseboard in a bedroom or a kitchen or a bathroom. There's just not enough wall space to do that. Sizing, we can go through it. Again, Hydronic does do a little deeper dive than we can do today in terms of the calculations. But the bottom line today is most heat exchangers are sized using software. Most manufacturers have this software available. I'm just showing you an example of one here. This is from Caleffi. It's called Flat Plate Select. It's free. You just go online, and I'm sure if you just do a search for Flat Plate Select, you'll find it. And you register for it. And basically, it's nice. You can configure what fluids, what flow rates, what temperatures are present in your, hypothetical heat exchanger, and it'll come back, it'll size the heat exchanger for you, or it will tell you, for example, if you've specified conditions that are creating unequal rates of heat transfer. That's the impossible condition. You can't send 100,000 BTUs per hour into a heat exchanger and get 105,000 out. So it checks for things like that. I found it to be pretty useful over the years, but again, other companies, I know Xylem, B&G has it, and I believe several other companies that offer flat plate. Alfa Laval is another one. Schwepp is another one. They would have similar or software for allowing designers to size up these heat exchangers. And quite honestly, you can do this so much faster than the manual calculations, and you can also do the what if scenarios and really kind of refine your design down. Okay, a couple other terms are associated with heat exchangers. One is called the approach temperature difference, and that's basically this temperature, the hot entering temperature of the fluid that's contributing heat to the heat exchanger, and from that you subtract the outlet temperature of the cooler fluid that's absorbing heat. In a perfect hypothetical heat exchanger, an ideal, unattainable ideal heat exchanger, these would be the same temperature. The fluid leaving the heat exchanger would absorb all the heat coming in, and it would have the same outlet temperature, okay? That's not going to happen, but the closer you can get the approach temperature difference to zero, and with flat plate heat exchangers, you can get it down into single digits. The better, the more effective your heat transfer process is. Now, another term that is less common, but it's an interesting term, called thermal length of the heat exchanger. What this is the temperature change of the fluid. Let's take one fluid. Let's say it's the hot fluid. It would be the temperature change of the hot fluid, okay, divided by the log mean temperature difference across the heat exchanger. And when we have fluids that are at very different temperatures, for example, let's say we have boiler water at 180 degrees, and we're transferring that into cold domestic water at 50 degrees. That's a huge delta T, and we would have what's called a very low thermal length. That's a very easy situation for a heat exchanger, and a relatively small heat exchanger could give you good rates of heat transfer under those conditions. But let's say we have a fluid at 120 degrees, and we're trying to transfer heat to a fluid at 110 degrees. Now we have a much smaller temperature difference, and that would be called a high thermal length situation. Typically, that's going to require a larger heat transfer area. And also, in a case of flat plate collectors, usually it's a longer plate rather than a shorter plate because of the ratio of the temperature change of the fluid divided by the available long mean temperature difference to create that rate of heat transfer. So again, you can put specific numbers into these formulas and calculate these out, but I put them in just so the terminology is explained here. Now here's another question we got. What's the closest approach temperature that can be practically used in hydronic systems? 1 in heating, 2 in cooling. Thanks. Well, again, it'll depend, but I put down here, it is possible to get it down in the range of about 2 degrees Fahrenheit, but you may find that not to be economically justified. Remember, as you bring this approach temperature difference down, you're doing that by using larger and larger heat exchangers, okay? So this is where you have to go back and look at what am I gaining, as an example, if I change from an approach temperature difference of 5 degrees Fahrenheit to 2 degrees Fahrenheit. In the case of a heat pump, transferring heat maybe to a fluid, an antifreeze, yes, the COP in theory would go up a little, but is that going up a little worth another whatever $1,000 on the heat exchanger? So again, you can't necessarily say I always want to design a heat exchanger for a 2 degree Fahrenheit approach temperature difference, absent consideration of what is it that you're accomplishing with that very close approach temperature difference, and what is it costing you to accomplish that. Some installation details. Here's a little 3-inch by 8-inch heat exchanger, and you can see it's got 3/4 inch copper tubing connected to it, and that tubing is connected to a strut rail system. That heat exchanger probably only weighs a couple pounds. It's probably got a coffee cup worth of fluid in it. There's no problem in terms of supporting the weight of that heat exchanger on that copper tubing, provided that the tubing is supported, I would say, within a few inches of the heat exchanger. I wouldn't want that cantilevered out 10 feet, but 6 inches to a foot in an area where it's not going to be, impacted by something, no problem. Now, when we get up into larger heat exchangers, this is actually that 5 by 12 by 100 plate heat exchanger. And you can see it's wrapped with 1/2-inch elastomeric foam insulation because it's going to operate in a chilled water mode with a heat pump. You see the steel brackets down below. That's just light gauge steel angle to support the weight of that heat exchanger. That heat exchanger probably weighs about 20 or 25 pounds. We don't want that weight all hanging on the tubing. Here's another heat exchanger, and if you look close, you'll see there's a little steel angle bracket down at the bottom supporting the weight of that. The piping itself is actually holding it in place there. That's not screwed up into the bottom of that heat exchanger, but it is supporting the weight. And then over here on the right, some heat exchangers are equipped with threaded steel studs on the one inner plate. So in this case, the installer just used some angle frame, angle material, and some ready rod and some nuts and bolts and held it together. So that's a nice support. Those are typically, those threaded studs are there. So a heat exchanger like this could be mounted, for example, in a vehicle where it's, it's subject to dynamic loads versus just in a heating system where it's just static loads. Now, Again, we talk about fouling factors. Here's a plate out of a plate and frame heat exchanger, and you can see it's got a lot of something. I'm not sure what that is, but it's got a lot of debris on it. And we don't want that. That's going to definitely increase that fouling factor and decrease the performance. You could use a Y strainer on something like this. Traditionally, we've seen a lot of engineering drawings that use Y strainers. Y strainers have to be opened up to clean the basket out. They do impose a pressure drop in the flow stream. You typically know when it's time to clean them by what the pressure differential is. That's going to go up over time. And they also require isolation. So if we're going to pull the basket out of that Y strainer, we've got to isolate it, which means that can't be flow in that circuit. That may mean the system is shut down. And then we take it apart, we clean the basket, we put it back together again. And I'm just showing you here that as Y strainers accumulate dirt, the resistance, the flow resistance definitely goes up. And that's not a good thing. That's simply using more pumping power. Or if the pump can't provide that extra pumping power, it's going to cause a drop in flow rate because it's adding resistance to the circuit. Low velocity dirt separators don't have these characteristics. The flow stream and where the dirt accumulates are separated. The dirt settles to the bottom and it's not going to impede the flow stream. And these can be blown down without stopping the flow or isolating the separator. And again, they're available today as what I call standard dirt separators, low velocity zone dirt separators, or with magnets. And the magnets are increasingly popular with the ECM circulators. They gather up very small iron oxide particles that can, under some circumstances, get in wet rotor circulators and cause some problems there. I would recommend you use a dirt separator on both sides of a heat exchanger. This is, again, a drawing that is elaborated on in Hydronics 29. You can see the dirt separators here are upstream of both the flow going into the heat exchanger as well as the circulators. So those dirt separators are protecting both. You also see that we've put some isolation and purge valves in this drawing. What those would allow would be to isolate either side of the heat exchanger. You shut the flow off, and you could connect up a flushing system to do an internal cleaning of some debris. Now, how effective that internal cleaning is depends what the debris is. If it's a calcium scale that's built up over a long period of time, you may be able to reduce it with an acid circulation, but you probably can't completely clean it off. But we do like provisions that allow flushing of the internal sides of the heat exchanger. And there's just a drawing. It shows a small submersible pump with some hoses flushing out one side of that heat exchanger. You can see it's isolated by the purge valves here, and then the hose bibs just give you the connections for that. Now, some freeze protected circuits. This is a pretty common application in hydronic systems. Here we've got a boiler going out to, let's say, floor heating in a garage. And perhaps the owners want the ability to just shut that heat off. Maybe they're going to, go south for a couple weeks. They don't want to heat the garage. They don't want to worry about the system out there freezing. So the area of this system that's in this pink box, this is operating on an antifreeze solution. It is a closed, isolated loop. As such, it does need an expansion tank. It should, by code, have a pressure relief valve on it. We need a means of adding fluid to it, as well as getting air out. And I would certainly recommend a good air and dirt separating capability within that circuit. Treat it just like you would any other hydronic closed loop circuit. Over on the left, this is water, okay? And again, it's a closed, isolated circuit. It has the same trim details. It does, in this case, has an automatic makeup water system on it. Now, this is actually using a variable speed circulator. We have some type of controller. It might be built into the circulator. There are circulators on the market now that have internal, internal circuitry that can look at a temperature sensor and try to maintain a set point. In this case, so we've got a temperature sensor here on the supply going to that floor heating manifold. And the speed of the circulator is going to go up and down depending on what the response at this temperature sensor is. If we're holding the set point right where we want it, the speed stays constant. If the set point starts to drop, we're going to speed up. We're going to increase the flow rate through that heat exchanger. Now, remember, that's not a linear change. If we double the flow rate through that heat exchanger, we're not going to get twice the rate of heat transfer, but it is going to go up. And if you've sized the heat exchanger for design load conditions, this under partial load conditions, the variable flow rate should, it's a closed loop feedback system. So it's a nice system. I've actually used this on garage heating applications. It works great. Here's another way to do it. You could do it with a thermostatic mixing valve rather than a variable speed injection system. I do want to stress here that we have got boiler protection. We've got a thermal protect valve. This is a thermostatic mixing valve. When you have a garage floor or any high mass load that could be at a very low temperature, even a sub-freezing temperature, you want to make sure that you don't hold that a conventional boiler in a sustained flue gas condensing mode. So using a thermal protect valve, that basically is protecting that boiler. It's keeping the boiler inlet temperature above the dew point of the flue gases. When a variable speed injection pump is used, the controller typically does that function. It monitors that boiler inlet temperature, and when necessary, it would slow that injection circulator down to protect the boiler as a priority over maintaining the supply water temperature. And again, these kinds of circulators have been used for many years now, commonly in radiant heating applications. Okay. So we get to some applications. And again, we could make all kinds of schematics, but here's an example of snow and ice melting as one of multiple loads in a system. We've got a couple ModCon boilers over here going into a hydraulic separator that is doing our, it's isolating our boiler circulators from any of our load circulators, but it's also doing air, dirt, and magnetic particle separation. And then we just come out basically to a header system. We have a variable speed pump here going off to zone valves that go out to space heating loads. All right. Down here, I'm showing a indirect water heater, and I've got the term prioritized load. We'll talk about that in a second. And then the other load is we're pumping through the primary side of a braze plate heat exchanger. And again, we have this pink box that represents the antifreeze portion of the system. We've got a mixing valve in here that is regulating the temperature going out to these circuits. And the important thing I want to stress to you is we are monitoring the water temperature leaving the primary side of the heat exchanger. One of the things you have to be careful about, okay, is imagine the antifreeze portion of the system. Let's say this garage has not been heated for several days and you're in a cold climate. You're in Caribou, Maine, okay? And that slab is at, let's say, 15 or 20 degrees Fahrenheit. Now, the antifreeze is still a liquid at that point. What's going to happen if we turn on this circulator, but either the boiler doesn't fire or perhaps there's a couple minutes of warm-up time required in that boiler, or perhaps the circulator fails? In other words, we're not going to have much flow of warm water going through the primary side of the heat exchanger. Now remember, these heat exchangers have a very high ratio of surface area to volume. And that's a good thing in most cases, but where it can work against you is how quickly you can freeze the water on the primary side of the heat exchanger. It can happen within a minute with very cold glycol going through the other side. And even though that may be an uncommon condition, it is a possible condition. And we don't want to freeze the heat exchanger and potentially burst the heat exchanger. So we're going to have some kind of control that basically doesn't allow the antifreeze circulator to operate until we have verified at least a non-freezing condition and maintaining a non-freezing condition leaving this heat exchanger. And it doesn't necessarily have to be a high temperature. It might be 40 or 50 degrees Fahrenheit, but we're verifying that we've achieved that temperature and that we're going to sustain some minimum temperature. If for some reason we drop back to the point where we think freezing could be a potential condition, we're going to interrupt flow or interrupt power to the antifreeze. So it's a small detail, but it's an important detail. And certainly that could apply in a snow melting situation. Anytime we have a high mass load that potentially could be at a very low temperature when it starts up. Now, I also want to mention the controls for this system would typically make domestic water heating a priority load. And the reason for that is the transient heat transfer rate to a cold slab, that can be very high. It could basically take all the heat that those boilers are producing and pull the water temperature in the rest of the system well below the temperature where domestic water could be heated. And quite honestly, if the domestic circulator, if this circulator was running, we could actually pull heat right back out of this tank and end up sending it out to our nice cold slab. So we want to have controls that when we have a simultaneous call for, let's say, heating that garage floor slab or that snow melting system, and we have a call for domestic hot water, the control should give priority to domestic water and probably the next lower priority to space heating. And as long as those loads are being satisfied, as long as we have adequate supply water temperature to meet those loads, then we can enable operation of the snow and ice melting system. Here's almost the same system. I've just changed it to a pool heating application. And here we're using a shell and tube heat exchanger. We've got modcon boilers, so we don't have to worry about sustained flue gas condensation, but we do have to be concerned about a fact that, let's say, a 20,000 gallon pool, that's a huge thermal mass. Again, if we have a simultaneous call for domestic water and we're dumping heat into this pool at maybe 80 degrees Fahrenheit, we could end up pulling heat right back out of that indirect water heater, because the pool basically is, I describe it as a black hole for BTUs. It's basically going to suck up BTUs wherever it can, and the result of that is going to pull the whole system temperature down. So you need controls, again, that would prioritize your other loads. I like to think of a pool heating load as a load. It's a load that you can do almost anytime within a 24-hour period as the lowest priority in the system. We could heat the pool at 3 o'clock in the morning because it's such a high thermal mass, the temperature isn't going to change very quickly. So think about the pool as a place to put heat after you've satisfied the higher priority loads, domestic water heating and space heating. And also only use heat exchangers that are rated for the chemicals in the pool water. Typically today, this is going to be titanium or a titanium stainless steel alloy on the tubes that are carrying the water from the pool. Don't use a heat exchanger with 316 or 304 stainless steel. It's not going to be able to hold up to the high chlorine content of that pool water. Okay. Now, same system, I'm changing it over to conventional boilers. Again, we want to make sure these boilers do not operate with sustained flue gas condensation. So a thermal protect valve, this is a high flow capacity thermostatic mixing valve. That is there to protect those boilers, to keep them operating above dew point and still allow all the heat output that they can provide. Full heat output is still going to the load, but the boiler is not sitting there operating with sustained flue gas condensation. And the balance of the system is the same. The pool, space heating, domestic water. We're using again, a magnet-equipped hydraulic separator, SEP4 unit between the boilers and the loads. High capacity domestic water heating. Commonly in residential hydronic system, we use indirect tanks with internal coils, and in most cases they work fine. But when you get up into several 100,000 BTUs per hour of domestic hot water demand, you're going to find it difficult to find an indirect tank that has enough internal coil surface to pass, for example, 750,000 BTUs per hour. Now that sounds like a very high number in a residential setting, but if you've got a house with, many bathrooms in it, you potentially could have a domestic water demand of 15, 20, even 25 gallons per minute. Do the math on 20 gallons a minute heated from 50 to 120 degrees, and you're going to be approaching, actually, you're probably closing in on 1 million BTUs per hour. So the limitation is going to be that internal coil and natural convection heat transfer, okay? Especially if you're using heat sources where you're trying to keep that heat source temperature down. So the option would be to go to a plate and heat exchanger. It could be a braze plate, or in a larger commercial application, it could be a plate and frame. But it's basically set up as a interface between the potable water in the tank. You do need to use a stainless steel circulator because this is potable water going through one side here. We want to make sure we have a check valve rated for potable water in that circuit, so we don't have reverse thermal siphoning when this circulator is off. And then over here, we're basically we're taking heat from our boiler plant, putting it into the primary side heat exchanger. Now, again, I want to stress, and I stress this because I've seen this happen in the field. This cannot be a little zone circulator. You can't move 800,000 BTUs per hour with an 80-watt zone circulator, all right? And some of you may be chuckling, but we've seen that as, installed hardware. You've got a flow bottleneck. You're moving 800,000 BTUs per hour, you're probably dealing with 2-inch pipe and some pretty high flow rates, 40, 50 plus gallons per minute, way beyond what a little zone circulator can do. So make sure as you size these circulators that you're sizing them for the flow rates that you need to affect the rate of heat transfer. And the idea is that you should be able to take every last BTU per hour that this array can produce and put it into that tank under reasonable temperatures and flow rate conditions. So that, again, we'd go back to the sizing software and do our what ifs, what size heat exchanger do we use in a system like that. And then over here, we're showing the, it's called the Legiomix station. This is basically a pre-set up with a Legiomix mixing valve in it that can do a thermal disinfection cycle. We've got a very simplified domestic distribution system here, but we're using thermal setter valves here. Again, one of the issues of Hydronics, I believe it's issue 21, but don't check that. One of the issues gets into using thermal setter valves as an intelligent way to control recirculation flow rates in a larger recirculation type domestic water application. Okay. Again, I'm showing purging valves. Again, these may be separate valves when you get up into larger pipe sizes, but the idea is to be able to isolate the potable side of the heat exchanger and do a mild acid wash is common to clean up calcium or magnesium scaling. I've had people tell me, these heat exchangers will foul out if you have hard water. Well, so will any water heater. If you have hard water, you simply can't complain that you're losing heat exchangers, whether they're internal heat exchangers, direct fire water heaters, or flat plate heat exchangers. You've got to treat the problem. Fundamentally, you've got to clean the water up or soften the water so that you're minimizing any accumulation on these. So flat plate heat exchangers can work really well for domestic water heating. But again, hard water is going to be the enemy of any heat exchanger. Real quick, we got about 5 minutes left here. This is a on-demand domestic water heating system where we have a buffer tank. And the buffer tank could basically go out to other loads, maybe some zone space heating loads. It's very simple. It's a braze plate heat exchanger, stainless steel, with a circulator. This circulator is operated by a flow switch. So whenever we draw hot water to a fixture, the flow switch would activate at some threshold flow rate, typically in a small residential application. It's around 3/4 of a gallon per minute of flow. I like to run it through a relay just to make sure we don't put high current into a reed type switch there. And we're turning on the circulator, and because our heat exchanger is very close to the tank, within about 2 to 3 seconds, we have the hottest water in the tank going right down through the primary side of the heat exchanger as cold domestic water goes up the other side. This has been used extensively in European markets. This is not a hypothetical concept. It's been used a lot. And the thing I like about this really minimizes the amount of domestic hot water that is maintained at temperature. So it reduces potential for Legionella. It reduces standby losses from tanks. And it's a nice way to get dual function out of a buffer tank. Normally we think the buffer tank is there to buffer the space heating loads, but we can also use the energy stored in that buffer tank and put some of that energy into our domestic water using this setup. Again, in the interest of time here, you can add an auxiliary heater to that. If you're dealing with perhaps a heat pump system, you may not be able to get that potable water all the way up to what the desired distribution temperature is. So you can incorporate perhaps an electric tankless water heater or some other type of water heater. It could be a tank type water heater there as well. So we're getting a preheating function out of our heat exchanger. I just want to show that this concept is available from actually multiple manufacturers now in commercial scale. That's a plate and frame heat exchanger, and it's got a recirculation pump. It's got a mixing valve here, a motorized mixing valve, and controls. This is simply taking that concept and scaling it up into much higher capacity, probably several 100,000 BTUs per hour, if not more than 1 million BTUs per hour. And I put that in because one of the questions we got, why not use a simple gas-fired water heater rather than a brazed plate and frame heat exchanger on a gas-fired boiler? Well, there's a number of reasons. When you go to separate combustion systems or separate heaters for domestic water and space heating, we have 2 burners, you need 2 fuel supplies, you need 2 vents, and you have 2 potential sources of carbon monoxide, all of which go down to 1 when we have a single burner system. The heat exchanger would store much less heated domestic hot water, reduced potential for Legionella simply because there's less volume there of potable water, potentially containing less microbes. The heat exchangers would allow for higher capacity. If you're up into multiple millions of BTUs per hour, it's going to be difficult to find a direct fire water heater. Now, again, you could use multiple direct fire tanks, line them up, but that's a lot of surface area. And that goes away with the instantaneous domestic hot water concept. So I think it's very viable both in a residential scale and also in a commercial scale application. I'm just going to say consult Hydronic 29 on this. It's kind of an interesting application involving on-demand domestic water heating as well as multiple separated electric tankless water heaters. And then it also has a provision for a thermal disinfection cycle. Just in the interest of time, though, I'll have you check that out. This is the alternative to the copper coils in the tank, the large thermal storage tank. We're using external brazed plate heat exchangers. Definitely stainless steel circulators because this is an open vented tank here. This is not a closed system. And also it's important up here, no vents or valves, anything that could allow air into the system because this is atmospheric pressure right here at the top of the water. That piping that has water in it above that water level in the tank is going to be under slight negative pressure. And the water will stay in that pipe unless air can come in. If there's an air vent there or a leaking packing on a valve, that will let that water drain back out. So it's a small but important detail. Okay. Again, this just shows how you can incorporate either a ModCon boiler or a conventional boiler into a system like that for supplemental heat. Basically, both the heat exchanger and the boiler are in parallel. All right. They can operate independently or they can operate at the same time. When you operate them at the same time, it's important to use a differential temperature controller. Again, Hydronic 29 gets into that in more detail. And finally, a district application. Okay. multiple boilers going to multiple client buildings. We're using heat exchangers to separate the buildings system from the district system. That's necessary because if we had a leak in one of the client buildings and we did not have heat exchangers, potentially the whole district system could go down due to that one leak. So most of these district systems have isolating heat exchangers at all the client buildings. All right. This same detail, adding a boiler in parallel with the heat exchanger. So if the central system, the district system is insufficient to supply the load, the auxiliary boiler could kick in. And we're using a heat meter there to keep track of how much heat is coming in from the district system. All right. Another final question, thoughts on variable speed pumps. Real quick, we talked about that already. Actually, one of those schematics, here's a variable speed pump controlling flow rate. It's not controlling the delta T across the heat exchanger. It's controlling the supply temperature on our load. I don't see, quite honestly, that the delta T control concept, I don't think it has as much merit as actually watching the supply water temperature. That is really what's going to determine whether your heating system is getting adequate heat transfer. Okay. Now, this is actually a Caleffi product. It's not in the North American market at this point, but it's called a heating interface unit. This does both space heating and domestic water heating. It has two small brace plate heat exchangers. And I put it in because it is variable flow as a means of temperature regulation. We're not using circulators, we're using valves, modulating valves. And the control unit will modulate the flow of hot water from the central mains that goes through either the space heating heat exchanger on the left here or the domestic water heat exchanger on the right. And that is monitoring, that controller is monitoring the outlet temperature on the secondary side of those heat exchangers and regulating the primary flow rate to maintain that. I think it's a pretty interesting idea. It's certainly a very compact unit. I think we will see an increasing market in North America for these. I've got two more slides here real quick. Both of these are in Hydronics 29. This is using a heat exchanger in a lake water cooling application. These won't be very common, but they are possible. The first thing you'd want to check out is any regulations about using lake water for building cooling. Certainly the temperature is there and the volume is there, but we don't want lake water going directly through our coils, our circulators, and so forth. So we're using an isolating heat exchanger. We're also going to have some type of filtering system. There are automatic filters that can detect if they're building up any kind of debris, and they will automatically do a backwash. So I would certainly look at, if you're contemplating this application, make sure you have an automatic filter that can minimize or hopefully even eliminate any debris from the lake that could get into the heat exchanger. And the last one, this is a company, I believe they're down in, I think, Alabama, Louisiana. They make what's called the lake plate heat exchanger. And it's a really simple idea. It's multiple stainless steel plates on a frame. It's immersed in a lake. And you can see there's high density polyethylene tubing. And basically this is a heat exchanger. It can either dissipate heat into the lake, or in the case of cooling, it can be the source of chilled water. And the nice thing about this is a closed system now. Okay, there's no need here to worry about debris from the lake getting into the system. So we do put a hydraulic separator in between the plate heat exchanger there, or the lake heat exchanger, and our cooling distribution system that lets us have different flow rates on both sides if we need to. Again, we could do a lot more sophisticated things with this. We could do variable speed control on this pump based on trying to watch the supply temperature over here and so forth. Okay, we are back. And Max, are you still here to take us home on this?
Sure. And I guess we'll go through the last couple slides, and then I've got a couple questions that we can go through from the chat. Okay. So this is our team based in Milwaukee. If you've got questions specific to a job, we always like to talk through that. A lot of the stuff that John's going through is great theory, and then sometimes you say, I'm standing in front of this. how can you help me? And all 4 of these guys are great with helping out with those questions. We also have a podcast if you haven't tuned in for that. So we've been going through kind of a rotating speakers. Dan and Greg are our hosts, and they've been interviewing people about topics that rotate. Really good information, something you can listen to in the truck on the way home or whatever. But the podcast is past 20 episodes, which is good. And then Cody Mack is doing, one of our trainers is doing the 5 Things You Need to Know series. This is one of my favorite things to pass along to really any audience. And in a couple minutes, he goes through just the really main things that you need to know about things like DHW, recirc creep, and questions we get all the time. That's kind of where we pulled these topics. But those are great. They're on YouTube. You can send those around to anyone that you like. And then follow us on all the social handles. Mary's always live tweeting stuff on Twitter from Coffee with Caleffi. And then we just had a really fun contest, an installation contest for Caleffi Gold for the Olympics that just wrapped up. We always like to post photos of your job sites as well. So send us all your cool sites and we'll brag about them on social media. Okay, so a couple questions. One of them I'm actually going to put right into the chat and send it around. So we got a couple questions about thermal length of the heat exchanger. So if you click on the link that I just sent you in the chat, that goes to our new digital hydronics, interactive hydronics, and you can scroll down to the bottom and click on thermal length of the heat exchanger, and that's going to be basically just that section. So the question, Siggy, is let's imagine that we have an on-demand heat exchanger and DHW recirc. Which thermal length should we prefer for a heat exchanger, long or short? So that's, I don't know that we have all the criteria that we need there, but if you want to just kind of address that at a high level.
Yeah, that's an interesting question. It would depend on, I think, what that return temperature on the recirc side is. So it would definitely would be higher than the cold temperature, but there would also be times when the cold water is going to come into that and blend into that mix. I don't know. We'd have to take specific temperatures and analyze it, but in general, the closer the two fluids are in temperature, you're preferring to go with heat exchangers that have longer thermal lengths to them. A good example would be, I think I used 180-degree boiler water on one side going to 50-degree domestic. That's a very wide delta T. That could use a very short thermal length heat exchanger. Whereas 120-degree water coming from a buffer tank going to maybe, in the case of, let's say, a recirc system, maybe 110-degree water coming back into the heat exchanger. That's a much closer temperature compared to the other situation. So I'd probably still favor looking at longer thermal lengths, but bottom line, I would run different scenarios in one of the softwares and just try what are likely to be the different entering water temperatures in that recirc system and just see what kind of results the software is suggesting on it.
Yeah, and I imagine the answer is probably different if you're in Vail, Colorado versus Orlando, Florida, with the water coming from the utility, that temperature too.
Yeah, the water temperatures, but yeah, again, it would depend if there's constant recirculation going on there. I would think the water temperature coming back into the heat exchanger, the system that I showed was basically cold water going into the secondary side of the heat exchanger and no recirc. I suppose it would also be possible to configure a system. Actually, that one slide that I did jump over, and it is in Hydronics 29 with the multiple tankless water heaters. That would probably be a good one to direct whoever asked this question. Take a look at that in Hydronics 29. That would show you the concept better.
Great. And then this one is might have a bunch of different answers too, but how can you identify failure in a plate heat exchanger? So there are probably a couple answers here, but
yeah, well,
over to you.
either a slowing rate of heat transfer, and you're probably going to you're probably going to get some type of a troubleshooting call. Like, for example, the garage isn't heating properly. I want the garage at 65, but my system is on all the time and I can't maintain the garage over 45. I would trace that back probably to inadequate heat transfer, and assuming that the heat exchanger was sized correctly and operated correctly initially, it's probably due to a fouling effect over time, which, if it can be cleaned, then you may be able to restore some of that performance. You probably won't get it, depending on how long the debris has been accumulating on the plates. If it tends to harden onto those plates, it may be difficult to clean it up. But I would think that one of the common failure modes, probably the most common failure mode in a heat exchanger, like a brazed plate heat exchanger, is simply a reduction in rate of heat transfer due to fouling. And taking the precautions of doing the dirt separation and provisions to do a periodic acid wash on a domestic water system, using demineralized water on the heat source side of the heat exchanger. Collectively, that should minimize the possibility of that failure. I mean, those units are pressure tested, and most of those brazed plate heat exchangers, they have pressure ratings like 300 PSI, in some cases even higher, well above the operating pressures, and also well above the common operating temperatures in hydronic applications. So a mechanical failure due to a temperature or a pressure situation, I would say, is pretty unlikely. It's more likely to be, if the failure, if you get inadequate heat transfer right from the get-go, the heat exchanger, it either wasn't sized correctly, or you're not getting the proper flow rates due to inadequate pumping. As I mentioned in the domestic water application, if you're trying to move several 100,000 BTUs per hour with a little 80-watt zone circulator, I mean, that's immediately the problem right from the beginning. If it's a scenario where, yes, I had adequate heat transfer initially, but over time it's gone down, it's probably a fouling related problem.
And then if you did have a leak, if you had a dual wall heat exchanger, you might have a wet floor right under that heat exchanger if it's a flat plate or a tank style or something like that. Or if you've got blue glycol on one side and that starts coming out the potable water tap, you've got a problem too.
You do. And I didn't mention, but brazed plate heat exchangers are available with double wall configurations as well as foil type heat exchangers that are used in some indirect tanks.
Yeah, great. Well, I think that takes us to the end of the questions. We've got some that we'll follow up with by email after the fact, but thank you again, John, for hosting. This was a great tour through a lot of different heat exchanger topics, and we will see you again soon. Thanks.
Thank you, Max.
Thanks, everybody.